Welcome to Circuit Analysis. I'm Jesse. Today we're looking at Ansys Maxwell. It's a 3D, 2D finite element analysis program, and it focuses on electromagnetics, so Maxwell's equations. It was built by a company called Ansoft and then sold to a company called Ansys, who sells it now. It has simulations like magnetostatic, electrostatic, eddy currents, transient, electric and magnetic, and AC/DC conduction simulations. So we're going to model a toroidal transformer. I just found this little toroid core in my garage, so we'll use that as an example. And the way we're going to do it is we're going to start with their PEmag program, which helps you build the 3D model, and then that transfers that to Ansys in a 3D or a 2D. So we'll go over both of those. And then we'll finish it off with some troubleshooting tips and tricks. So here's what we're going to go over. First, we're going to do the PEmag program, define the core and the model, and then we're going to transfer that over to Ansys Maxwell in a 3D and a 2D model. Then we can configure that model in Maxwell. So we'll set up the material properties of the core and the wires, and we'll set up the excitation waveforms. So that's the waveforms that are flowing through the wires, and we can do that with a constant or with a lookup table, or we'll show how to do the simpler circuit simulator. It's an embedded kind of SPICE-like simulator. So then we'll set up the mesh, which is the finite elements in the model. So you're breaking the geometry into these finite elements for the finite element analysis. And then we'll enable inductance and core loss, and we'll set up and run the simulation. After that, we'll have the outputs. There's two types of outputs that you can plot. There's the results, which are 2D plots or tables, and then there's the field overlays, which lets you put results into the 3D space as vectors or overlays on top of the geometry. So here we are in PEmag. We're going to make a new file, and you see it's got all these sections. So here we're defining the transformer model, and this is really nice because if you want to model a 3D object just from scratch, it takes a lot of work and a lot of finagling around. But this here is set up to do it for us. So we have this properties section, this thing with all these tabs here, and then this is kind of the main design section. This is where you'll see what you're doing. So we can start over here with the core, and they have all these predefined cores here from common manufacturers. I happen to have a little core that I just found lying around here. So it's a 55047 toroid from Mag Inc. So I was thinking we'd model that. If you look in here, you got toroids. 55047 is not listed in here. So this will be a good opportunity to make our own. Now the way you do that is at the top of this, there's this component library here. So when you drag stuff into that, then that's what you're going to use for this model. So if they don't have it in here, you can come into the default library and default toroidal core, and you just put that up here. Just hold down and drag it. Now you can double click on it, and we can give it a name here. So we're going to call it 55047. And here is where you got to look up all the information on it. So we've got the data sheet here for that core that I downloaded off the internet. And then we just have to go over here and fill in the information off of these area, volume, length. So if we first go to these other tabs here, you can edit in here these dimensions. So we can see here D1 and D2 are this one's outer diameter and inner diameter. And this here we have it set to millimeters. So we can do 12.7 and let's see, 7.62. And then D3 is this height here, so that's 4.75. Now we'll leave all of these 0 for now. And then back here, and this thing's pretty finicky here, hard to use, so I gotta re-enter this guy. And the AL here we can see is 90. And these dimensions here are gone now. You have to hit apply a lot. Oh, it's given me this error now. AL must be a valid value, so we can just open it again, give it another shot. So we've got 90, apply. Let's just close it. Let's see. All right, so it's got 90 now. We'll try putting this in again here. Apply. Okay. Yeah, so it's kind of working. So we got 12.7, and now we want 7.62 and 4.75. Oh, if you hit enter, it disappears. So got to start over. 4.75. So don't hit enter. Hit apply. And if you see these weird characters here, don't worry about it. They'll disappear. They're still here now, but if you click like OK, and then you go back, see, they're gone. Anyway, you can have it calculate, but what you're going to notice is the area, the length, the volume, they don't exactly match up with what we have over here. So like here is the length 31.9, 31.2. Area, let's see, so volume here is 340, here it's 385. And the reason for that is because this core over here, it's showing it as like a sharp edge, sort of a cutout from a tube, maybe like a square cross section, whereas this one over here is more of a torus, more of a round cross section. Not exactly round, but I think I'm just going to leave it for now. Well, what you can do is you can put these in here, and then these you can overwrite. So we'll just say the cross-sectional area is 10.9 right here, and then the length is 31.2, and now we calculate that up. 10.9, 31.2. Okay, it automatically adjusts this one, so 340. So now we have this. So these dimensions over here are not exactly lining up with this. And I think when you transfer it over, it pretty much just uses these dimensions. So this here is just not even going to really matter for what we're doing. So in the material, you can define some stuff here, but I don't want to calculate that because it's just going to overwrite this one over here, I think. So we'll hit OK. Now that we have that set up, go to the bobbin. We don't want to be bobbin because it's a torus winding. So in the winding here, we're going to want to set up one winding and just use their default. Now this is a little confusing here the way this works, but you set up your windings here and then sub-windings. And each one of these is really like a layer. So when we double click on this, I'm just going to call this all. And you have pins, which are down here, just how many ends of windings you have. So let's just do 2 windings. So we'll have a primary and a secondary, and that's it. So we're going to have 4 pins. And then the layers here, we're just going to have 2 layers to start with. Now, we'll do 3 layers to start with. So the first layer is just going to be a little spacer around the core, like we put coating with 0 on the core, so that'll be kind of simulating the coating. Let's see, I think that's good. You can add more and then move them under each other. So now, this one here, we want to define wires and insulation. So we're going to do, let's see, round wire, default insulator. All right, so the default insulator, we're just going to call this coating and make the thickness, so we got 50 micrometers. And this here, we can just leave the rest the same. Apply that. So it's unhappy because it needs thermal conductivity must have a valid value. So I'm just going to make this 1 and we'll make this 0.9. So we'll apply that. Okay, these aren't really going to be very relevant for our simulation. For the wire, we might have different size wires and different thicknesses and stuff. For this one, let's just call it 30. So if we get a wire gauge chart, it's going to say the diameter for this is about 0.254. But you can see the way that this is kind of measured. The W includes the insulation. So I'm thinking if we put on here, let's do like 25 right here, 25 micrometers. And we're going to have to add that to this. So that's going to make this become 3 right here. So that's the actual width. And then this turn spacing, we're going to leave for now, but I'll show you we can adjust that later to kind of space the wires more evenly around the core. And now it's giving me an error because these wire conductivity values are 0 here. And you know what I was just thinking is this is kind of a waste of time because, let's see if I can get rid of this. It won't let me end it now. I have to make these 1 or something for it to go away. Now the whole thing's freaking out. Okay, so that's gone. But what I was just realizing is there's a ton of models for wires. So we can just use AVX or mag round. Here we go. AWG 30. So we'll just drag that up here. Round. And then we can delete this one. Just hit the delete key. Get rid of that. So we can see what they have in here. So they've got basically the same similar stuff here, and then they have these guys filled out. And these aren't really going to get transferred, or we're not going to use them in the 3D model again, so it doesn't really matter. It's mainly just these geometries. All right, so now we get to the core material. And this one is, we're also going to redefine this, so it doesn't really matter. But if you look into magnetics, we can find iron powder, just because this one is an MPP core. Can do this 200 mu down here. Add that up here for the component library. So now we have everything defined here, and it's time to define these layers. So this first one here we said is going to be an insulator around here. So we go over here to this wires and insulation. Drag that up to here. See that change to insulator material coating. They all start as insulators. We don't want these to be insulators. So we define them up here. Since it's a flyback, we're going to do the first one clockwise, the second one counterclockwise. See the 2 little dots? And now we're going to drag this 30 gauge up to here. And you can see it popped up a little wire right there. Now we'll drag this one up to here. Now I can see both of those wires. Double click on here. All right, so you right click on here. Right click brings up the properties. Sometimes you double click, sometimes you right click. All right, so number of turns. We're just going to do 10 on both of them. So that's okay. Now you can see there's 10 here. And this one here, 10 as well. And that's really not a whole lot. So maybe we'll make it 20. You got to be careful if you get them both selected. So you just want this one. There we go. So now we have 20 of each. And you'll notice that they are, you can right click and left click to zoom in and out of this. You'll notice that they are on separate layers. So this one here is the first layer inside, and this one's the one outside. So if you want to get them on the same layer, you have to make this one a sublayer. So go up here to, let's see, one of these moving things, move selected sublayers. So we're going to move this one here, and now they're all lined up together. So that's taking up about half of it. Now we can go into this material, and this is where we can adjust the spacing. So we'll do 0.1. See what that does. So that gets it a little closer. It is like 0.2. It's getting a little closer. So while we're doing this, you want to check out this design status. So this has a bunch of problems here. So layer 2, sublayer 1, node 1 has no connections. Okay, so these are connection problems, and that's because we have not connected these wires here yet. We can go ahead and do that. So this is the connection here, and we're just going to connect the first one to the top, second one to the bottom, and you do have to be careful of the polarity here. We can check it in 3D model, but we'll just do the first one to the top, second one to the bottom, and if we follow it all the way through, it should work, because this one has a different polarity than this one. Right click to get rid of that tool. Now like everything is fine. So we want to extend this coating. You can see is very short here, and the wire could go a little further. So we're going to go to 5, and that's almost there, to 8. So 2.8 is technically still okay. I'll just show you real quick. If we do 0.3, they're going past each other here. And that doesn't matter so much, but these ones are overlapping. So it's not going to like that. See, it doesn't fit, it says. So you're not allowed to have them overlapping. And we can go in here and do 2.75. So that looks pretty smooth. And now for the coating, go back here to all, right click on that. We change the height. So if we make this 10 millimeters, see it starts to go further around. Make that 25. 25 is a little too far. So 20, not quite enough. 24, let's see, yeah. So 20, we'll just do 23. 23, maybe. Yeah, you see there's a little tiny gap there. Yep. So that fits pretty well. So here's our transformer. It's not super exciting, but you get the idea. We've got 2 windings, one on each side. So now we're ready to export it to Maxwell, but there is sort of an intermediate check we can do if we want to just make sure that this model makes any sense. Yeah, it's not really necessary, but you can go here to Modeler. You do the 2D here, Start Model Generation. And this will build a whole model, and it'll run a little simulation of it, and then we can view the results. So now that pops up this model generator here. We just click Start. And this here is going to build a whole model, and it might take 10 or 20 minutes. So I'll just show you when it's done. Alright, so it finished. I think it maybe took 8 minutes or so. So it looks like it'll tell you it's done. And then it's got this stuff that pops up, and it gives you some resistance and inductance. But I don't think these values mean a whole lot right here. So we're going to do exit. And we'll exit this. Now we get back to PEmag. And we want to go results and look at the 2D results, the DC resistance and the Lmag. So the AL was 90. So if we go in here and do 20 squared times 90, so that's 36,000 nanohenries. So here we have 37 microhenries. So it all kind of makes sense here. And then we have a few milliohms for the resistance. Okay, so we can close this, and we're going to go Modeler. This is the Maxwell 2D 3D link, so we're ready to export this. And I don't know why the two options are eddy current and electrostatic. There's a bunch of different simulation options, but eddy current is one of the magnetics ones, so we'll do that. And we have here 2D or 3D. We're going to start with the 3D, and this applies symmetries. What it'll do is it'll chop the bottom half off of this, so you're looking at it head on, and it kind of reduces the computation by just mirroring it. But for this, we're not going to do it. It'll take longer, but we'll just do the full model because we're not really worried about speed. And then in the second part, we'll do the 2D, which is way faster anyway. So we'll do OK. Yeah, so this is the version here. It's 2022 R2. It's kind of fun. While it's generating it, you can see it makes the core. It makes the wires one at a time, piece by piece. You can see what it's doing is it's making each winding separate. So it's not like an actual transformer where you wind around and around and around with one strand of wire. It's modeling every winding as a separate geometry loop. So that is one simplification it's making. You notice, like I was saying before, the transformer is not a torus necessarily. It's more like a slice out of a pipe. So that's it for the PEmag. I think we'll end it here for this video. In the next video, we'll do the 3D simulation in Ansys Maxwell. And I'll put a link in the description. I'll put these videos in a playlist, so if you're not in the playlist, you can get that and make sure you're watching them in order. Thanks for watching. See you next time.